All right. So speaking of this, I think we've done magnetism, and we should start induction now. I believe so. Probably yeah. Second please. Right, kids. So we're gonna start with electromagnetic induction today. Let's do that. So speaking of electromagnetic induction, then first of all, what you guys need to remember is that we have to learn what is the magnetic flux. Magnetic flux is the total number of magnetic field lines that pass through a given area. So, magnetic flux can also be sort of defined as the product of magnetic field strength V and the perpendicular area A. It's a scalar quantity, and the SI units for magnetic flux is Webers. It's written as WB, by the way. Capital W, small b. So magnetic flux has this symbol, which is called phi. And like I said, it is the product of magnetic field strength and the perpendicular area. This is for only a single turn. What I mean by this is, like if you look at the wire, it sort of goes like this. Is it clear, everyone? And then the magnetic field is going through it, like that. So when you have a mini turn thing, we call this as magnetic flux linkage. And magnetic flux linkage is magnetic flux that links through हाँ हाँ तो करो ना, तो बनाओ। मेरे पास तो बेटा नहीं पड़ी, उसको कहो कि कैनवास बना दे। So magnetic flux that links through a coil of N turns, which means that now the total flux that links is going to be BA times N. We can also write it as flux times N if you like to do that. This N, by the way, is the number of turns. So suppose you have a coil that has many turns, and the field is going like that. This is known as magnetic flux linkage. Please write this down, and if you have any questions that you want to ask, please do. All right, kids, you have any questions now?
No.
All right, just give me 1 minute while you copy this. I'm just gonna get some water. I'll be back. All right, everyone. So now, for this one, it's also very important to understand that the linkage must be made at 90 degrees to have a full effect. What do I mean by that is that suppose you have a magnetic field going in this direction, and then your wire is exactly, it looks like this, like that, okay? Or your wire could be at a certain angle to it, or it is also possible that your wire is completely parallel to the magnetic field. In this case, the wire is at 90 degrees from the magnetic field, and then this one as is at a certain angle theta, and this is basically at 0 degrees, which means that the magnetic flux here is going to be like that, and here the linkage is going to be BAN sine theta. Why do you need sine theta? Because you want to find what is the
The vertical component.
yes, perpendicular component. Very good. When it is completely parallel, because no field is interacting with it, which means now the magnetic flux linkage is going to be zero, because if you put in sine zero in the calculator, it's going to give you a zero value. Is that clear, everyone?
Yes.
Now, what you guys need to remember, it's very important, and that is that all these things have this whole chapter depends on the two different laws. All right, these laws basically govern everything that we're going to do ahead. The first law is called the Faraday's law of electromagnetic.
So can I copy the diagram first?
Yes, please, why not? You guys can copy.
Done.
Okay. Now, if you basically look at the two laws, first we're going to learn about Faraday's law, and the other law is called the Lenz's law. So let's look at both of these one by one. They're highly important. So, according to the Faraday's law, it says that the rate of change of magnetic flux linkage rate of change of magnetic flux linkage is directly proportional to EMF induced. Alright, kids. Now, the keywords that you guys need to focus on would be the rate of change, flux linkage. That is something that you guys need to remember, because in IG we used to just get away by change in magnetic. Okay, so basically, the EMF induced is proportional to the change in magnetic flux over change in time, like that. So you guys need to remember that. In IT, we used to write change in magnetic flux only. So that's now in the past. We need to be very specific now. Now, interestingly, when Faraday gave this law, it is not 100% accurate, although he talked about the right thing. So the lens, basically the other scientist, he said the law has a big issue, and he said that the direction of induced EMF that he's talking about is always such that to oppose the change that is produced. So basically, he told everybody that the EMF must be in the opposite direction of the change that is causing it because it needs to oppose it. Is it clear, everyone? So here, this is a negative sign which shows the opposition. So you guys need to remember that. Both of them won Nobel Prize. First, because he gave the concept, the other just putting a minus sign. So that was correct. Do you guys get it?
Yes.
I'm actually moving to Canada in like end of November. So I'll take it classes only for a month because obviously in Canada there's like the whole different course. I just don't want to sit empty for a month. Alright, that's not an issue. Okay, is it clear, everyone? Should I go forward now?
Yes.
Okay. Now let's try to understand what these two laws really tell us. So imagine that we have, you guys have written this? Should I go forward now? Okay. So first off, let's talk about, suppose there's a coil or solenoid that's put right here, and this coil has been attached to a sensitive galvanometer or an ammeter, whatever you have. It's okay. And then there is a magnet which rests here, the north here, south here, and the magnet right now is stationary. So I'll copy this and then I'm going to explain this to you. So, first of all, you guys need to understand that basically, if you look at the magnet, it's just very far and its magnetic field is barely reaching the solenoid. So, there's little or no flux there. Do you guys understand that? And because there is little or no flux in this, so that would mean that there will be no current seen in this one. And doesn't really matter if there's a flux or not. The important part is that the current is zero because there is no change in magnetic flux linkage. So there's no change actually. So it's just staying constant at zero or maybe a little bit. It's like just there. Is that clear, everyone? Okay. Now, speaking of this, then he then basically said that because the needle was right here, he then noticed that when this magnet started to move in a direction towards the uh, coil itself. So Faraday observed the faster it moved, the greater the deflection caused. And the reason is that if you check the relationship, it's basically change in magnetic flux over change in time. So there's a change happening because it's coming nearer to it. So there will be more interaction now. But then if you take a less amount of time, you will get more EMF induced. Is it clear, everyone? And he said, if there was no relative motion, all right, if there was no relative motion between coil and magnet, no EMF was induced. For example, if I put it right here, and when I've moved it, so now first of all I'm gonna make it here. So there was a deflection, and current was now not equal to zero when it was moving. But now if I bring this closer and make it stationary, now I have the magnet really close to it, but now it's just stationary because although the flux is the maximum right now because the field goes through the coil completely, but then because there's no relative motion, then obviously it won't have any effect on the EMF because it needs a change in magnetic flux. Do you guys understand this?
So is there motion after relative in the third point?
There's no motion, huh? Stationary, so there's no relative. Oh, okay, relative motion, yes. Do you guys understand that?
Basically, in the third point, we could say that both the magnet and the coil are moving in the same direction with the same speed.
Even if they're moving in the same speed, same direction, there's no relative motion, no EMF, because you need to change the flux. If the flux is staying constant, whether it's zero or maximum, it doesn't induce EMF. It doesn't induce EMF. Is it clear? Then what he noticed was that when this magnet was moved in the other direction, like it's right here right now, and now it is moved away from it. So right now there is no current, but when it is moved away, it started showing current in the opposite direction. Do you guys understand that? So he said that if, now this is what Lenz has said. So Lenz has said if the direction of motion is reversed, the deflection occurs in the opposite direction. Is that clear? Now, why is that? Because I'm just going to write it in different color because the EMF or current induced in the coil is such that to oppose this change. Now, how does it oppose the change? Let me just talk about it here. You see, when it was moving towards the coil doesn't want this magnet to come near it. So it will create its own induced knot on this side such that to repel the magnet away. In order to do that, the kinetic energy of this magnet is taken up as work done by the electrons to oppose this, and now what happens is that the current will start to move in such direction to create a knot to oppose this. Do you guys understand that?
Yes.
And when the magnet was moved away, so it needs to oppose this change, so it will try to attract it back. So it will create a south here so that the kinetic energy of this is converted into the work done to slow it down into this coil, and now it will create current in opposite direction to stop it from moving away. This is the reason the current direction reverses if you change the direction of the movement of the magnet as well. Is that clear?
Yes.
Good. So this is the combination of how this whole thing works, and there will be a couple of other examples. There will be things that you would be asked. Just don't worry about it. It's okay. Are you done, kids?
Yes.
Still doing last one.
Okay. You can draw the drawing. It's okay. Okay, should I go forward now?
Yes.
Okay. Speaking of this then, we're now interested in sort of a solution here. So I'm just going to give you an example of a falling magnet. So let's suppose you have a coil. So you have a coil like this, which is like that. Okay, it's better. And now this coil is connected to maybe an ammeter, like that. And then let's make three positions of it. And they've shown basically a magnet that is falling through this coil. Like there is a north here, there's south, it's just falling, and then it's still falling inside. This is a very important example, by the way. It will help you understand a lot of stuff. Like that. It's still moving with velocity v, and then it has gone through it completely. It's still moving. Okay. Now, what do you expect the current to be in the first one? Like, do you expect current to be there?
Yes.
How? Because what's gonna happen is because the field is like this, right? Field is like this. There's a change in flux happening. So the north will be created on this side, south will be created on this side, which means it's gonna oppose it. So there will be a current that's positive this way. Is that clear?
Yes.
When it is moving through the coil, do you think there is current? What do you guys think?
No,
Why?
because the
Why
number
no?
of magnetic field lines will remain the same.
Because when you draw the field in the previous, chapter, we drew some fields. They look like this, right? Do you guys agree? Actually, what's
Yes.
happening is that now in this whole section, if you see here, the field, while it's going through the coil, the field strength is not changing at all. So the flux is not changing, which means there won't be any current. Current will be zero. Do you guys get it? The current will be induced
Yes.
when it has completely exited the coil, because now south will be, now north will be created on this side to attract it back, south on the opposite side. So the current will be induced, but in the opposite direction. So this is one of those examples that I wanted to share with you, and I wanted to basically put this concept forward so you guys know that when it is going through, right in the middle. There won't be any current because there is no change in magnetic flux happening here. All right, then please draw this. Now the question is that even though we know that the kinetic energy, because it's trying to slow down, so the kinetic energy is going to do work done in on the electrons, so within that coil. So when there is work, there must be a force and some movement. Do you guys understand that?
Yes.
So now we're going to learn how this movement is made within a conductor. This is pretty simple. So once you've drawn this, I'd like to move to the new page actually. All right, kids, should I go forward now, please?
Yes.
Okay. So going to the next, let's look at that then. So in this one, I'd like to tell you, so it will be oscillating magnet in a coil. Oh no, this will be later. Sorry, my bad. First of all, I need to show you that. All right. So we're gonna say movement of electrons, or you can also write charges within a conductor moved in a magnetic field. So we're looking at basically a magnetic field. which is infinitely large and uniform, like that. It's also perpendicular to a conductor like that. And the length of the conductor, suppose, is L, and we are moving this conductor perpendicular to the field. So it's basically 90 degrees to the field. Is it clear, everyone? Here,
Yes.
you can write it is magnetic field into the page. Now see this. Now this is just a conductor. It's not connected to anything else. Nothing else here. When it is moved, basically you guys need to understand that the electrons will feel a force because of the magnetic field itself. How? Because we know that force on electrons is equal to BeV. Basically, it's the formula that comes from BQV. I'm writing E because I want to show you the charge on an electron. Is it clear?
Yes.
So the direction of force is found out using Fleming's left hand rule. So you can basically put your index finger towards the page, your middle to the right, so your thumb will be up. So that's true for a positive current. So the electrons will start to move downwards. Is that clear? You can check as well.
Yes.
Because of this force, when the electrons move downwards, these are the electrons, they tend to make this side, this end, as negative and this end as relatively positive. Do you get it? You can call this end as P, you can call this as end Q, so that we can have a, this. And then when you connect basically a voltmeter across this, so this voltmeter is going to show you the potential PQ, where there's a potential difference that has been created right here. Understood?
Yes.
So we can say that as electrons are pushed towards Q, Q relatively becomes negative and P positive. Okay. You can attach a voltmeter across it to find the potential difference. And that's how we know the current has moved from one point to another. All right. Please write this down and draw this, and then I'm going to go to the next.
Yeah, said I have another Quran class right now.
Oh, I just saw the time is up. I'm sorry about that. I should have not started this. Anyway, so we will then, do the derivation later on. All right, kids. So have a nice day then.
Thank you, sir. You
We'll
too.
continue tomorrow. Bye.
Thank you. Bye.